Now here's a quick pop quiz for you. Decimal 255 is equivalent to which binary and hexadecimal values? So decimal value of, so remember a binary, so remember a byte with all, so remember that Hey everyone, welcome back. Today we're going to be talking about the difference between high-level programming languages such as BASIC and low-level programming languages such as machine code and Z80 assembly language. But first I want to read a bit of an excerpt from this book, Z80 Machine Code for Humans, which was printed in 1983. So you can see, well, I believe that old books still have some value, particularly for someone like myself who is just starting my journey on this path of learning to develop games for the ZX Spectrum Next. And what I want to read first is on page 143 of this book, Appendix C, which is labeled A Comparison of Basic and Z80 Machine Code. And the reason I want to read this is because I just ran across this and it seems to describe pretty much the topic of today's video perfectly. And it encompasses the ideas that I'm going to be explaining a little bit. So let me just read this hopefully quickly to you, and it'll give you an introduction to what we're going to be discussing. So it says, BASIC is a fully developed system designed to make the writing of programs quick and simple. As such, it carries heavy overheads in terms of program execution speed and memory usage. Machine code programming, on the other hand, can achieve the maximum speed available from the processor and make the most efficient possible use of memory at the cost of increased programming time and greater complexity. The ease of writing programs in BASIC or in machine code is a qualitative difference, a matter of opinion rather than hard facts. The average programmer will prefer to work in BASIC, and yet a skilled machine code programmer with a good assembler and a comprehensive subroutine library may well find BASIC the more difficult to use. A direct comparison can be made only on the quantitative differences of speed, timing, accuracy, and storage efficiency. Timing, accuracy, and storage efficiency. Machine code is the language of the processor. The slowness of BASIC is due solely to the tremendous amount of work it has to do when interpreting the programmed commands and keeping track of all the variables. The greater power of machine code programs is gained only by the programmer taking such tasks upon himself, or herself, and not paying the price charged for letting the machine do all the work. So that pretty much exactly describes some of the attributes of high-level and low-level programming languages, in particular BASIC and Z80 machine code. It talks about how BASIC is easier to use because it uses commands that are closer to the English language. For example, if you're familiar with BASIC, you already know that it uses words like for, next, let, save, load, print, all words like that that are essentially English words that humans can easily understand. Whereas machine code uses codes, it uses numbers, and those numbers might be in hexadecimal or decimal or even binary, but it's kind of difficult to understand a program that's written entirely in codes, which is why programmers prefer to work in high-level languages, such as BASIC and other high-level languages. However, why is machine code, well, interesting to use for programming and useful to use for programming? Well, machine code, as the book just mentioned, is much faster than BASIC. And the reason for that is because BASIC is what's known as an interpreted language. So the first thing we should understand is that computers only understand machine code. That's the only programming language that computers understand. They don't understand BASIC or even assembly language. All they understand is pure machine code. And any program that's written in any programming language other than machine code either has to be translated into machine code first, such as with assembly language that we're going to be discussing in a moment, or in the case of BASIC, needs to be interpreted or translated on the fly as it's running. So BASIC, since it's written in pretty much English words, which the computer doesn't understand, in order for the computer to actually execute a BASIC program, it needs to translate or interpret each command line by line as the computer is executing the program. So if you think of it such as compared to two people who are trying to communicate, and you have one person trying to communicate with another person, but they speak different languages. The first person might be trying to explain a set of instructions to the second person, but in order for the second person to understand it, they need an interpreter, someone to translate. So as the first person is speaking, everything has to be translated through the interpreter in order for the second person to understand it. So that takes a lot of time, and with computers it takes a lot of machine cycles and time again. So it's very slow in order to do all that interpretation on the fly in real time as the program is running, which is why BASIC executes so slowly. Now, that's not to say that BASIC is a bad language. It's a very good language to use, and I've used BASIC, and I'm familiar with BASIC. I'm not an expert in BASIC, but I have a basic understanding of BASIC, let's say. So even though it runs more slowly than machine code, it is still a good language to use, particularly if you're using it on the ZX Spectrum Next computer, for example, which has not only an enhanced version of BASIC, it has a version of BASIC that's called Next Basic, which contains more functionality and more commands, I believe. But also the ZX Spectrum Next computer runs a lot more quickly, or a lot faster than the original Sinclair Spectrums did back in the day. The original Spectrums ran at, I think, 3.5 megahertz, and the ZX Spectrum Next can run at up to 28 megahertz. So you could write very effective and good programs in BASIC. However, I am interested in trying to write some games in Z80 assembly language, mainly because I haven't done that before. So it's something that is kind of a challenge for me, and I think I would find it interesting, and I would really like to see how we can get the most, well, at least speed out of the computer. But I just think it would be something interesting to learn. And there's actually something in this book that I found where it describes my sentiment about that as well. So right here in the preface, actually, it says, "We do not pretend that machine or assembler language coding is better than coding in some high-level language. It all depends on what you want to do and the resources you have at the time, particularly the time for doing it." And that's exactly right. So if you want to program in BASIC, then there's nothing wrong with that. If you want to program in machine code, it will probably take more time, I guess, depending how familiar you are with machine code or assembly language. But as it mentions later on this page, the satisfaction that comes from working with the instruction set that actually controls the computer, rather than through somebody else's translation or interpretation, is something that must be experienced to be understood. Personal computing is about more than getting applications programmed quickly and easily. It is partly about the pleasure and satisfaction to be gained from exercising your mind. Hard mental effort, like physical or spiritual effort, has its rewards. Now, we mentioned that machine code is the only language that computers understand. So what about assembly language then? How does an assembly language program get executed by the computer if the computer only understands machine code? Assembly language programs have to be converted or compiled or assembled into machine code before it can be run. So that's why they run so quickly, is because the entire program is converted into machine code before it even starts running. So you're running a pure machine code program by the time it even starts running. But let's talk about assembly language a bit more. And again, I'm going to use this book as an example because it's coming in very handy so far, so I think I'll continue on with that. So if I look at the back of this book, it has a section where it describes the Z80 instruction set. And those are all the instructions that the Z80 microprocessor understands, and those are the instructions that we would use to make our assembly language programs. And let's take one just as an example. So although I haven't learned assembly language yet, I am familiar with a few of the commands, and one of the commands that I know is the return command, which is probably the command that everyone learns first, or maybe the org command, which tells the computer where to start storing the program, but we'll talk more about assembly language after I actually learn it. But one command that I'm familiar with is the return command. And basically what that does is you put that command at the end of your assembly language program, and it returns control of the computer back to whatever called the machine code program. So for example, if you're writing a basic program and then somewhere in that basic program you call a machine language subroutine, then once the machine language program finishes and it hits the return command at the end, it returns control of the computer back to the basic program, or whatever called the machine code subroutine to begin with. And if we take a look at it here on page 129 of this book, you can see right here is the return command, and then over here next to it, it shows the code for the return command, which is listed as C9 in hexadecimal, which is why we learned all about hexadecimal in our last video, because it's going to be just as important for us to know as binary. So this return command is abbreviated as RET, which is known as a mnemonic. So machine code, pure machine code, uses codes, it uses numbers. So the C9 code, for example, would be the machine code version of this assembly language command return. So if you wanted to program, let's say in pure machine code, you would enter this C9 code, this C9 hexadecimal value, into your program. And this would be a machine code program, not an assembly language program. If you're writing an assembly language program, then we would use this assembly language mnemonic, it's called, RET, which stands for return. And the reason we use assembly language, as I'm sure you know, is because it uses these sort of pseudo-English mnemonic words that are easier for humans to read and to understand and to remember. But if you were programming in machine code, you would have to type in this hexadecimal C9 or its equivalent in some other number system like binary or decimal. So while we're talking about it, why don't we see if we can practice converting that hexadecimal value C9 into its equivalent decimal value? Well, how would we do that? And let's try and do that in our head without using any calculator or computer or anything. We'll just see if we can do it all manually with our own brain power. So we know that each hexadecimal character can be represented by 4 bits, which is otherwise known as a nibble. So if we say that the C is over here on these 4 bits and the 9 is here on these 4 bits, so we have a hexadecimal value of C9. Well, the 9 we don't really have to do anything with because it's already a decimal value of 9, right? So we can just remember that the 4 lower bits, otherwise known as the low nibble, have a decimal value of 9. So what about the 4 high bits, or the high nibble? What do we do with that? Well, we know that has a hexadecimal value of C. And what is the decimal equivalent of C? Do you remember from our last video? Well, A has a value of 10, B has a value of 11, and C has a value of 12. So already we know that C has a decimal value of 12, right? And if we want to convert that C into binary, and we know that it has a decimal value of 12, these 4 bits have the values of 1, 2, 4, and 8. So if we take 8 plus 4 and add them together, already we have our value of 12 right there. So we know that if we convert our hexadecimal C into binary, it's going to have 2 1s in the top 2 bit positions and 2 zeros in the lower bit positions. So it would be 0011 to get our hexadecimal value of C. Now, in order to get the decimal value of the entire byte, we need to combine these 4 bits with these 4 bits that we had originally, which is the 9, right? So this was a C, and this was a 9. So we already know this decimal value is 9, and this decimal value is no longer 12 because now we've combined these 4 bits with these 4 bits, right, to make it an entire byte. So these are now the top 4 bits. And do you remember what the values of the top 4 bits in a byte are from our last video? Well, the lower 4 bits have values of 1, 2, 4, and 8. And then these high bits would have values of 16, 32, 64, and 128. And remember that our C converted to a binary nibble that has these 2 bits turned on, and these 2 bits have a value of 64 and 128. So if we add those two together, 64 plus 128 gives us 192. So if we add that 192 value to our 9, 192 plus 9 gives us a total decimal value of 201. So we now know that our hexadecimal value of C9 has an equivalent decimal value of 201. And that was pretty easy to do, right? Just all in our head. We just thought of it without having to use a calculator or a computer or anything, and it was pretty painless, wasn't it? So I think that's a pretty useful skill to have, to be able to convert between different number systems manually. Just by thinking about it, if you can convert between binary and decimal and hexadecimal and back and forth between them in your head, I believe that will make our programming task much easier if we don't have to constantly use a calculator to do those calculations for us. Okay, so before finishing off this video, I thought we'd do something interesting, which is, let's take a look at 2 programs doing the same task, one written in BASIC and one written in machine code. Now what this program is going to do is fill the entire screen with a character by loading that character into the video display. Now we're going to be covering the video display memory in an upcoming video, and we're also going to be looking at the programs that I use to create this, as well as how to set up the programming environment on our computer to actually enter these programs and see them running. So first let's take a look at this program running in BASIC. And here's a listing of the program on the screen for you to take a look at if you want. If you're familiar with BASIC, then this is probably very obvious what this program is doing. And if you're not familiar with BASIC, then you don't really need to worry about the code at this point, because we're merely interested in seeing the comparison in speed difference between a program running in BASIC and a program running in Z80 machine code. But basically what this program does is it fills the entire screen or screen memory with the same character. So here we've just set up a simple loop that cycles through the entire screen memory, which ranges from memory location number 16384 to location 22527. And we're poking that location, which means we're entering a value into that location of decimal 183. And if you're able to convert the decimal value of 183 into binary, you should have an idea of the pattern of bits that is going to show up on the screen as they get plotted onto the display. So let's go ahead and run this routine and see how long it takes to fill the screen. So there we see the program running, and it's filling the screen byte by byte with this particular value, which gives us this unique pattern. And as you can see, it's filling the screen in thirds and then filling those individual thirds line by line. Now, if you're not familiar with why it's exactly filling the screen with this pattern, then don't worry about that. We're going to be covering that in an upcoming video when we talk about the display memory and the memory layout for the ZX Spectrum Next computer and the Sinclair Spectrum computers. But for now, just take a look at how quickly, or rather slowly, it's filling the screen with this pattern while running in BASIC. And there it's finished, and that took about 45 seconds. Now let's take a look at the same program running in Z80 machine code. Now I'll show you a listing of the Z80 assembly language program I'm using to create this pattern, just in case you happen to be interested. But again, at this point, we don't really need to understand these commands yet in our programming journey because we're going to be covering all that in upcoming videos. But I thought I would provide it here just for your reference in case you're interested to see it. And the way we execute the program in this case is by using this command randomize user 50,000. And again, we don't need to know exactly what that's doing at this stage in our journey, but all we need to know is that it's executing a machine code program that has been saved starting at memory location 50,000. So let's go ahead and run this and see how long it takes to fill the screen. Wow, that's a big difference from the basic program, which took about 45 seconds, to this one, which filled the screen instantly. So you can see right there, that's an obvious example of how basic is much slower compared to machine code, and how if we want our programs to run quickly, it may just be worthwhile learning to program in machine code. So that's pretty interesting. If you would like to help support this channel by becoming a Patreon subscriber, head over to patreon.com/spriteworks and check out the different subscription levels. So thanks for watching, and we'll see you next time.